All right, so let's jump right in with the derivative power rule. And this says that the derivative of x to the n is n times x to the n minus 1. All right, so there is the derivative power rule. Now what this really says is that when you take the derivative of a power, x to the third, is that the power will come down to the front as a multiplier. So you'll get 3 and then x, and then we're going to subtract 1 from the power. So 3 minus 1. Now normally you'll do that subtraction in your head and you'll simplify this down to 3x squared. All right, so let's take a look at another one. The derivative x to the fifth. Okay, again, the idea is that the 5 is going to come down to the front, and then we're going to subtract 1 from the power. So we're going to get 5x to the 5 minus 1, or 4. Now, where we really start to unlock the versatility of the power rule is when we realize that lots of things can be written as x to a power. For example, if I'm taking the derivative of the square root of x, I can realize that the square root of x is the same thing as x to the 1/2 power. So in this way, the derivative of the square root of x becomes the derivative of x to the half. And now it's x to a power, and I can use the power rule. So again, the power rule says the 1/2 is going to come down into the front as a multiplier. So we're going to get 1/2, and then x to the 1/2 minus 1. Now we do that arithmetic, and we're going to get 1/2 x to the 1/2 minus 1 is negative 1/2. All right, now we can rewrite this if we need to, as first of all, the negative pushes that x to the bottom, so 1 over 2x to the half, and then that 1/2 power again goes back to a square root, so 1 over 2 square roots of x. All right, well, let's take a look at another one. Let's say that we're taking the derivative of the cube root of x. Okay, so again, all we have to remember is that a cube root is the same thing as a power. We can rewrite this as the derivative of x to the, this time, 1/3 power. All right, and now we can just apply that same power rule. The 1/3, that power comes down as a multiplier, so 1/3, x to the 1/3 minus 1, or 1/3 x to the minus 2/3. Okay, let's take a look at one more involving roots. So let's say that we're taking the derivative of the 4th root of x to the 5th. Okay, so what I'll see a lot of students do in this case is they'll realize that that 4th root is the same thing as a 1/4 power, and they'll rewrite this as x to the 5th to the 1/4 power. And then they'll do a power rule for the 1/4, and then end up having to use a chain rule to handle this x to the 5th on the inside. Now you might be able to get the correct answer this way, but it isn't using the full potential of the power rule and laws of exponents. So instead, what we want to remember is that we have a rule for converting roots directly into powers. And that is that when you have the mth root of x to the n, that mth root is called the index of the root, or the type of root that you have, and that's going to become a denominator of a power. So for example, a square root is a second root, and you'll have a 1/2 power, whereas a cube root is a third root, and you'll have a 1/3 power. And then this n, the x to the n, that's just going to go into the numerator. So the mth root of x to the n is going to become x to the n over m. So let's take a look at the derivative of the 4th root of x to the 5th again, utilizing this rule. So now it becomes the derivative of x to the 5/4. And now it's just a power, one single power, not a chain rule, and we can bring that power down as a 5/4 multiplier, and then we're going to subtract 1 from the power. So 5/4 minus 1 is 1/4. Okay, so much simpler, and we don't have to use a chain rule in this situation. The next example that I want to take a look at is for taking derivatives of very simple fractions, say something like 1 over x cubed. Now, remember that we can't simply take the derivative of the top and the bottom. That is not a derivative rule. Now, we do have something called the quotient rule, specifically designed for derivatives of fractions, but that's really overkill in this problem. Instead, what we want to remember is there's a law of exponents that allows us to move powers of x from top to the bottom simply by changing the sign of that exponent. So 1 over x cubed is the same thing as x to the minus 3. And again, I haven't taken a derivative here yet. All I did was use my laws of exponents. And now the derivative of x to the minus 3, the power comes down, negative 3, and then x to the negative 3 minus 1. Now we do have to be a little careful subtracting from a negative, so just do be careful on that, but we'll get negative 3x to the minus 4. Okay. Now depending on the problem, we might want to leave it this way. Let's say if we're taking another derivative, or if it wants us to simplify, we could reuse that law of exponents and rewrite this as negative 3 and move that x to the minus 4 down to the bottom, and it'll become a positive power. So negative 3 over x to the 4th. Let's take a look at another example utilizing both the rules that we've used so far. So let's say we're taking the derivative of 1 over the square root of x. Okay, so what I need to realize is that I can rewrite this as a power. So again, the square root of x is the same thing as x to the half. And then because it's on the bottom, if I want to write it as an x to a power, I need to switch the sign of that exponent. So again, not taking a derivative here yet. The derivative of 1 over the square root of x just becomes the derivative of x to the minus 1/2 power. Now, once I've rewritten it as x to a power, now I can just use the power rule. So this will go to negative 1/2 will come down, and then we'll subtract 1 from that power. Minus 1/2 minus another 1 is negative 3/2. Now really the key lesson in both of these examples is that we always want to simplify. Use those laws of exponents before taking a derivative. Okay? So again, use the law of exponents, simplify, distribute, move powers up to the top before taking derivatives. And this will really help you unlock the power of the power rule. All right, let's take a look at a couple more examples using this simplification technique. So let's say that we're taking the derivative of 2x to the 4th over 3x. Again, remembering that we can't simply take the derivative of the top and the derivative of the bottom separately. Instead, we want to simplify. And really the form that we're looking for is we're looking for a constant multiple times a power of x. So for example, this 2/3, it's all just one multiple, and I can write that out in front. Okay? And now we just need to remember our law of exponents that says when we divide two powers, we're going to subtract those exponents. So overall, we're going to get 2/3 x to the 4 minus 1 or 3rd power. Okay, and again, we still have not taken a derivative here yet. I'm going to use the prime notation on this one. Okay, so now that 2/3, the constant multiplier rule, says that that 2/3 just sits there. And now this 3 can come down as a multiplier, so 2/3 times 3. And then we're going to subtract 1 from the power, 3 minus 1, okay, or 2. Now we can simplify this down a little bit. These 3's cancel out in front. We're going to get 2x squared. All right, let's take a look at another example. So let's say that we're taking the derivative of 3x squared times the quantity 5x plus 7. Okay, now we could use, again, the product rule, but what we want to do is remember that mantra to simplify before taking a derivative. So in this case, we can simply distribute this 3x squared before taking the derivative, okay? And we'll have 3x squared times 5x is 3 times 5 is 15. And x squared times x, we're going to add those exponents and get x to the 2 plus 1 or x to the 3rd, okay? And then plus, we'll distribute over here to the second portion. 3x squared times 7 is 3 times 7 or 21x squared. Now again, all we did was simplify. We still need to take the derivative. Now when we're taking the derivative of constant times a power of x, this 3 is going to come down, and again it's going to multiply. It's a multiplier. So we can do that multiplication in our head or using a calculator. First, we'll have 15 times 3 is 45, and then x to the 3 minus 1 or x squared. Okay. For our second term, the 2 will come down. Again, we'll multiply. 21 times 2 is 42. X to the 2 minus 1 or x to the 1st. Okay, So again, it's important that we want to simplify before taking a derivative. It really does help us out and avoids things like product rules or quotient rules when they aren't necessary. All right, let's take a look at a complicated looking problem that actually is pretty easy if you unlock the full potential of the power rule. So let's take the derivative of 7x to the fourth minus 3x squared plus 5 all divided by 2x squared. Now what you'll see is a lot of students will use the quotient rule to do this problem. And while that will work, if you just remember the mantra to simplify before taking a derivative, it will make the problem a lot easier. Okay, so to simplify this, what we need to do is remember that when you have a mononomial or a single term on the bottom, like we have here, 2x squared, it can divide into all the terms on the top. And it can just do this separately. And what I like to do is I like to think about the constants being divided and then worry about the x's. So for example, on the first one, 7x to the fourth divided by 2x squared, we'll just do 7 divided by 2 is 7 halves. And I really want to write that in front as a constant multiplier. And then x to the fourth divided by x squared, when I divide two powers, I subtract the exponents. So I get x to the 4 minus 2, or x squared. Okay, for our middle term, minus 3 divided by 2, again, that's just a constant multiplier, so minus 3 halves. And then x squared divided by x squared, that just goes away, okay? And our last one, 5 divided by 2, well, that's 5 halves. And then over x squared, but again, I want to write this as a power of x, so x to the minus 2. And now, remember, we still haven't taken derivative. All we did was simplify. But believe me, this is way easier than doing a quotient rule. Do the quotient rule, and you'll notice that you have to simplify at the end, and it's way more work than what we're doing right here. Okay, so now these power rules. The 2 comes down as a multiplier. We're going to get 7 halves times 2. When we do 7 halves times 2, the 2's are going to cancel. We're just going to get 7. And then x to the 2 minus 1, or x to the first. Okay. The derivative of negative 3 halves, that's just the derivative of a constant, and the derivative of a constant is 0. I'm going to write it here just for space, okay, so you know where that 3 halves went, okay, so it goes to 0, okay. And then our final one, the minus 2 comes down. We'll get 5 halves times negative 2 will become, well, let's just write that out, 5 halves times negative 2, and then x to the minus 3rd power, okay. We can simplify this down. We'll get 7x to the first, or just 7x. These 2's will cancel. You'll get 5 times negative, so minus 5, and then x to the minus 3 power. Okay, and you'll see that that's way easier than using the quotient rule. So again, always simplify before taking a derivative. It's really going to help you out. Now, where this simplification technique is super important is when you're using it on integrals or antiderivatives. So let's revisit the antiderivative power rule. And that says when you're taking the antiderivative or the integral of x to a power, you're going to add 1 to the power and then divide by that new higher power, which you can write as 1 over that new higher power in the front. Okay? So another way is the exact opposite of the power rule for derivatives. Instead of multiplying by the power and then subtracting 1, you're going to do the exact opposite in the opposite order. You're going to add 1 to the power and then divide by that new higher power. So for example, if we're taking the integral of x squared dx, okay, again, we're going to add 1 to the power, so x to the 3rd, and then we're going to divide by that new higher power or put a 1/3 out in front. Now, integrals typically do have this plus c term on the end, which I may or may not write on some of these examples. But let's take a look at another one. Let's say that we had 3x to the 6th, okay, dx. Again, the 3 is just going to sit there as a constant multiplier. We're going to add 1 to the power, so x to the 7th, okay, and then divide by that new higher power 7, okay, again, plus c. All right. Now, again, we can use the same rules that we're using before. Let's say that we're doing 1 over x squared, and we want to do the antiderivative of this. Okay, again, there is like an anti-quotient rule, but it's pretty complicated. It's called integration by parts, and we really only want to reserve that for the most difficult integrals. Instead, I can rewrite this just as I would with derivatives as x to the minus 2. And now that same exact power rule works, where you can add 1 to the power. So negative 2 plus 1 is negative 1. And then divide by that new higher power. So 1 over negative 1. Okay, now we can simplify this a little bit. 1 over negative 1 is just negative 1. And then x to the minus 1. And again, if we want to, we could rewrite this as negative 1 over x. All right, so the power rule for integrals, it's very versatile. It works for the integral of x squared, or the integral of x cubed, or the integral of 1 over x squared. However, it doesn't quite work for every power of x, and that's because we're dividing out here in the front. And when you're dividing, you have to make sure that you're not dividing by 0. And if we look at that, 1 over n plus 1, we just need to make sure that n plus 1 is not equal to 0, and that implies that n is not equal to negative 1. Okay, so our full power rule says that, again, we integrate a power, we add 1 to the power, and we divide by that new higher power as long as the original power wasn't negative 1. Now, if that power was negative 1, the integral of x to the minus 1 dx is actually the integral of 1 over x dx, which is known to be the natural log of technically the absolute value of x plus c. Okay? So that's what we do if that power is negative 1. Now, even more so than when you're taking a derivative, when you're taking an antiderivative, it's very important to simplify your powers before starting. Okay, so let's say that we're taking the integral of 7x to the 4th minus 3x squared plus 1 all over 2x squared. Okay, this looks very similar to the derivative problem that we did, but when we're doing an integral, there's pretty much the only way we can do this is by simplifying and then just using some power rules. So again, what we want to remember is that this monomial on the bottom, single term, nothing being added in the bottom, can be divided into each of the terms on the top. And again, we can separate that division into the constants. So 7 divided by 2 is just 7 divided by 2. And then our powers, x to the 4th divided by x squared, we can subtract those two powers and just get x to the 4 minus 2, or x squared. Okay, now in the middle we have negative 3 divided by 2, that's negative 3 halves. And then x squared divided by x squared, those just cancel. Okay. Finally, it divides into this last term on the end. We're going to get 1 half. Again, just do the constants first as a constant multiplier. And then 1 over x squared becomes x to the minus 2. And that way we can actually use a power rule on it. All right, so now, again, the constants just sit there. And then the power rule is that we're going to add 1 to the power, so x to the 3rd, and then divide by that new higher power, or write a 1/3 out in front. Okay, now the integral of a constant, technically you can use a power rule by writing this as x to the 0, but it's a good one to know that the integral of a constant is just the constant times x. So the integral of negative 3 halves is negative 3 halves x. Okay. Our final one, again, the 1 half just sits there. And again, it doesn't matter if we have integer powers, negative powers, or half powers, things like that. The power rule works. We can add 1 to the power, so negative 2 plus 1 is negative 1, and then divide by that new higher power. So dividing by negative 1 is the same thing as multiplying by negative 1. You'll get the same result. So I'll just write a negative 1 here. Okay. Now we can simplify all these constants. In the front, we'll get 7 halves times 1/3 is 7/6. X to the 3rd minus 3 halves x, and then 1 half times negative 1 is negative 1/2, x to the minus 1, and then plus c, of course, at the end. All right, now if you like this video, please take a moment and like it, and then subscribe to my channel so you can get more math reviews in the future.